Hello everyone. My name is Baiju Political and I work for Cisco Systems in the Advanced Services organization. So our team basically deals with customer support activities for the major cable MSOs in the United States as well as some of the cable service providers abroad. So the purpose of today's tutorial is to provide a high-level overview of DOCSIS 3.0 technologies. So the session which we are going to cover assumes some basic level of knowledge on cable as well as the prior DOCSIS technologies. However, as I start going over this session, if you have any questions in particular, please feel free to stop me anytime, and then I'll try to answer them. So I am not going to go through all of the acronyms and abbreviations listed here. This is mainly for the purpose of future reference when it would be archived and available on the NANOG website. However, I'm assuming most of you are familiar with what DOCSIS stands for. It is Data Over Cable Service Interface Specification. Cable Labs is one of the industrial consortiums which was formed by all the major cable multiple service operators like Comcast, Time Warner, Cablevision, and even the second tier operators, as well as the vendors who develop products in the cable industry to standardize the technologies, which was formed around 10-15 years back. And originally, Cable Labs came with the first set of specifications known as DOCSIS 1.0, then followed by that they released DOCSIS 1.1, and eventually they had a DOCSIS 2.0 release with every new version having more and more enhancements in terms of specifications to cover the additions of technological enhancements. And the latest set of specifications released by Cable Labs is DOCSIS 3.0, and it addresses a lot of business requirements today. Cable industry has got to account for the increased demand in bandwidth for the end subscribers, as well as to provide support for IPv6 addressing, enhanced security at the access layer, the cable broadband being the access layer. So to make sure that there is additional security enhancements introduced as well. So here is the agenda. We will just go over what is the motivation behind going for DOCSIS 3.0 specifications and the associated technologies, and followed by a brief overview of DOCSIS 2 or the prior DOCSIS version. I'm going to just talk about it on a single slide, and then we will go the modular CMTS architecture and how that plays a key role in supporting the DOCSIS 3.0 services. In the DOCSIS 3.0 overview, we would cover some of the key new features introduced with DOCSIS 3.0. One is called downstream channel bonding. Then we do have the upstream channel bonding feature also introduced with DOCSIS 3.0. And as far as the multicast support in the cable network is concerned, what are the enhancements which are introduced in DOCSIS 3.0 compared to prior versions of DOCSIS? We will take a look at that as well, and then we'll get on to the changes made in the 5-layer technology for DOCSIS, and finally we will talk about security as well as OSSI aspects, the changes made prior to the previous versions of DOCSIS. And as I mentioned, in addition to the channel bonding, IPv6 for cable support is one of the major enhancements in DOCSIS 3.0 compared to prior versions of DOCSIS. So obviously we will touch upon the relevance of IPv6 in cable access networks as well as certain operational aspects and how to implement that. So these are some of the business objectives behind going for DOCSIS 3.0. So as far as the bandwidth requirements are concerned, as we know, the end end subscriber bandwidth requirements are increasing on a day-by-day basis, right? Depending upon all the new applications coming up and the video streaming and whatnot. So the prior DOCSIS versions, DOCSIS 1, DOCSIS 1.x and DOCSIS 2.0 has got an inherent limitation on the bandwidth because at the most a single downstream channel wasn't able to support more than around 37 Mbps in the downstream, and that downstream channel itself is shared by multiple subscribers, right, n number of subscribers. And likewise, the upstream channels also had bandwidth limitations. So the solution DOCSIS 3.0 which came up with to address that was, instead of making a cable modem connect to single downstream channel or single upstream channel, make the cable modem connect to multiple downstream channels and multiple upstream channels, and then make use of a technology called channel bonding feature, which is nothing but multiplexing the data into multiple channels, keeping the multiple physical channels as a single logical bandwidth pipe, thereby enhancing the available bandwidth. And from the security perspective, there were requirements to provide enhancement to the data encryption, which was already supported in DOCSIS 2.0. So we will take a look at some of the security enhancements in DOCSIS 3.0. And another major requirement, business objective, was the IPv4 address will play a depletion. As everyone knows, the IPv4 address has the addressing limitation, right? And we are running out of the IPv4 addresses at a very fast pace. And there were specific requirements as far as addressing is concerned for MSOs to come up with a more larger addressing capacity to be available. So IPv6 for cable support was introduced with DOCSIS 3.0. And I mentioned about the modular CMTS architecture, right? And one of the key advantages the modular CMTS architecture brings in is it breaks the dependence of the downstream and the upstream channels, thereby contributing to lower cost when it comes to adding more and more channel into the cable plant. So let us take a quick look at what we had with the prior version of DOCSIS, which is DOCSIS 2.0. So in United States we have 6 MHz channels available for downstream, and Europe, as we know, it is 8 MHz. And in the downstream direction it supports 64 QAM as well as 256 QAM modulation order. But today most of the MSOs are implementing 256 QAM modulation order itself because their plans are capable of supporting it. And if they go with 256 QAM modulation, they get a throughput of approximately 38 Mbps in the downstream direction for a single downstream channel. And as far as upstream rates goes, what is the upstream bandwidth available for a single upstream channel depends upon the characteristics of the channel configured, and one is the channel width and the second one is the modulation order. We have seen that in the downstream the channel width is fixed. It is 6 MHz channels due to its historical reasons, right? Because always analog televisions were televised by using 6 MHz channels. But in the upstream with DOCSIS 2.0 it supports a range of channel widths ranging from 200 kHz to 6 MHz, and it also supports different modulation orders, QPSK, 16 QAM, 32 QAM as well as 64 QAM. So the actual upstream throughput, what is available on a per upstream channel basis, would depend upon what is the channel characteristics configured. If you have a channel configured with a channel width of 6.4 MHz and the modulation order of 64 QAM, you can get a channel bandwidth of as high as 30 Mbps. However, on a per flow basis, when one of the cable modems in the subscriber premises tries to transmit in the upstream direction to upload some information, it used to have a limitation typically of 1 to 3 Mbps because of the fact that there is a request grant latency involved. Because in the upstream direction, the technology used is time division multiple access, because a single channel is shared by multiple devices sitting at different subscriber premises, and the TDMA mechanism uses a bandwidth request which is sent by the cable modem devices, and the bandwidth grant needs to be issued by the CMTS before the cable modem can transmit something in the upstream direction. And one of the drawbacks with that request grant mechanism was when cable modem needs to transmit some information and it requests for bandwidth, it has to wait until unless the CMTS provides the bandwidth or it times out. It cannot send back-to-back bandwidth requirement. So that is why there was a request grant latency involved, and typically limiting the upstream throughput per flow to around 3 Mbps. However, there were fine-tuning mechanisms available to increase the throughput beyond the 3 Mbps by tweaking certain default parameters in DOCSIS. So this slide just talks about the typical implementation on the plant side. Typically, the distribution network consists of optical fibers which goes all the way to a neighborhood, and once it reaches the neighborhood, a fiber node converts the optical signals into electrical on an RF cable. And the fiber node typical penetration is around 500 ohms, but it can vary depending upon the particular MS of implementation. And this is where, depending upon what kind of services you offer and what is the subscriber density, right, the requirement for bandwidth on a per fiber node can vary. And sometimes the node splitting or adding more channels will be required to address that. And in DOCSIS 2.0 and prior DOCSIS versions, in a single MAC domain, a single downstream interface used to get associated typically with 4 upstream channels, and the single downstream would be fed into 4 fiber nodes. That is 4 different neighborhoods serving the same downstream. However, each fiber node would be provided with a separate upstream channel, which used to be a typical deployment scenario. Any questions on the DOCSIS 2.0?
Yeah. Is there a typical bandwidth that's used in the U.S.? You talk about all the different encoding and potential bandwidths. Is there a very typical use in the U.S.?
For downstream or upstream?
Well,
for as far as downstream is concerned, the US always needs to use 6 MHz channel width.
okay.
Because the cable plant, our television transmission is using 6 MHz channel width, and with 6 MHz channel width, you can go for either 256 QAM modulation order or 64 QAM modulation order. So if you go with 64 QAM modulation order, it's because it uses 6 bits per symbol, you would get around 27 Mbps per single downstream channel. And if you go with 256 QAM, because it uses 8 bits per symbol, that would be around 38 Mbps. So that is a single downstream channel can offer. And as you can see in this example scenario, that single downstream channel is feeding around 2000 homes, right? And not every single home has got an HSD or high-speed internet access. That would be maybe around 1000 or so. So, n number of subscribers are sharing a single downstream channel in that scenario.
Okay. And so what's the usual upstream, again, what's the encoding and what's the
So,
in US?
So in US, originally they started with 1.6 megahertz channel width, and then nowadays the plans are, there are a lot of upgrades done with the existing cable plan to support channel width as high as 3.2 megahertz, and if it is DOCSIS 2.0 they can go even 6.4 megahertz. So when you look at the upstream transmission, the transmission from the CM to the CMTS, the available overall bandwidth for a single channel would depend upon, as you know, the channel width plus the modulation order, right? So you have a range of modulation orders available, and until recently, a typical deployment like Comcast or Cablevision or Time Warner were using 3.2 megahertz channel width and 16 QAM modulation order. That would give you a throughput of approximately 10 Mbps for a single channel. And what we have to keep in mind is that 10 Mbps is shared by multiple cable modems trying to transmit information back in the upstream direction. And today, Comcast and Cablevision and even Time Warner are in the process of deploying something called Advanced Time Division Multiple Access, or ATDMA, which is part of the DOCSIS 2.0. And with ATDMA, you can go with 6.4 megahertz channel width and 64 QAM modulation order, and you can get as high as 30 Mbps per channel. It is shared again, that's the key. So the sharing thing, the way it works is, depending upon, you can consider that as something like the CSMA, but slightly different. Here, what is going to happen is, if a cable modem has some data descent, it has to request for bandwidth using a shared segment of the bandwidth set aside in the upstream to request for bandwidth, and then based upon the QoS configuration and the channel utilization and other factors, the CMTS will have to explicitly grant the bandwidth so that the modem can transmit the data it needs to transmit. Does that answer your question?
Yeah.
Sure. Now let us take a look at the concept of modular CMTS. So until DOCSIS 3.0 and the core specifications and related specifications were introduced, most of the CMTS implementations out there were using the integrated CMTS architecture. In an integrated CMTS or ICMTS, as you can see, the layer 2 and layer 1 functionalities are housed in a single system. So the integrated CMTS has got the DOCSIS MAC, DOCSIS layer 2 and upper layer protocols, as well as the downstream PHY, right, for sending the signals in the downstream direction, the modulation in the downstream and up conversion, as well as the upstream PHY for receiving signals in the upstream direction, and demodulation and then PHY layer processing. Everything was taken care of by a single entity called the integrated CMTS. So now moving on to the concept of modular CMTS. The modular CMTS architecture itself is divided into phase 1 and phase 2, and what is defined in the spec today is phase 1. However, the phase 2 is under development by vendors like Cisco, and sooner or later there would be a standardization on the phase 2 also coming in. So let us take a look at the modular CMTS architecture here with phase 1. So what you see here is, if you look at the MCMTS core, the DOCSIS MAC and upper layer protocols still reside in the MCMTS core device, and upstream PHY layer component also resides in the MCMTS core. However, the downstream PHY has been moved out to an external entity called an EQAM or HQAM, and this EQAM or HQAM is not a new device. It's out there in the cable networks for video streaming. Typical cable implementation for digital video streaming, what they do is they get the video signals over GIGA uplinks into an EQAM, and then the EQAM will take care of modulation and up conversion of the video signals to make it into RF signals. Now the same HQAM which has been there in most of the networks is going to take care of an additional function to process the DOCSIS downstream layer as well. So obviously when you move the downstream PHY functionality from MCMTS core to an external device called an EQAM, then you need to have an interface defined, right, to standardize. So in order to make sure that different vendor tiers will work without having to use any proprietary implementation. So the downstream external file or downstream external file interface or DEPI interface, what you see here, was defined to address the protocol and interface requirements for transporting the layer 2 information, layer 2 DOCSIS information from MCMTS core to the HCOM. And once it reaches the HCOM will take care of collecting the layer 2 information, DOCSIS frames, and then convert them into file layer, doing the modulation and upconversion functionalities. And DRFI or downstream radio frequency interface is another spec defined to standardize the file layer interface for the DOCSIS, and that is what is used in this model. And one more logical component which you see here is a DOCSIS timing server. And some of you who are already familiar with DOCSIS knows that the timing requirements in a DOCSIS network are quite stringent because of the fact that in the upstream direction, the transmission is controlled by the CMTS, and cable modems and CMTS needs to have strict timing alignment. And there is something called a ranging process which is used to acquire that. However, now that we have put some of the physical components to an external entity, then you need to have a centralized timing server which provides standard clock to both the MCMTS core, the external HCOM, as well as any other logical entities which come into play. So as you can see, the DOCSIS timing server uses a DOCSIS timing interface to provide DOCSIS standard timing information to the MCMTS core as well as ECOM to make sure that these two entities are in timing synchronization. Sure.
So your downstream nodes, how do you see the MCMTS core and the downstream PHY? Is this separate devices at layer 2 or is it one?
You mean downstream PHY?
Yeah, do you see the downstream PHY as a separate layer 2 device?
Yeah, the downstream PHY is taken out of the MCMTS core. So there is no downstream PHY processing which is done by the MCMTS core.
So the MCMTS, the ECOM, is seen as a separate layer 2 device.
Right.
So that means that any downstream node now needs to maintain a separate. How do they handle its sensing?
Right.
It's like taking a pick out of juniper and you just move it across the room.
Oh, okay.
But I don't understand what the win is, so could you talk maybe why is that? Why is it beneficial to remove
Yeah, why
the phi?
So,
change the phi.
So one of the things is like because it allows different vendors to go ahead and build ECOMs, for example, and then make use of it. Cisco doesn't have to come up with its own ECOMs, even though Cisco has got it, right? And another thing is HCOMs are already there, widely deployed, which are being used for video. And a lot of the HCOMs out there, well, all what we need to do is to do the software upgrade to support this functionality. And maybe some slight hardware upgrade with hardware cards and stuff, right? And what we are trying to accomplish with DOCSIS Leo is increased channel capacity. So to increase the channel capacity, you need to add more and more downstream channels. By decoupling the PHY components into a separate chassis makes it more easier to have a scalable architecture wherein as required you can keep adding the PHY components.
What is the physical interface to the EPI specification?
Yeah, that is going to be covered in one of the subsequent slides. Any more questions around the MCMTS model? So let us take a look at phase 2. The only difference you would see here compared to phase 1 is, in phase 1 we might have noticed that only downstream 5 components were decoupled and moved on to an external entity, right? With phase 2, what we have done is not only the downstream 5 components, but even the upstream 5 components have been moved to an external entity. So if you have something like a phi shelf, which represents this econ, so you can add downstream phi and upstream phi cards as required, right, as the network evolves. And in addition to that, when it comes to MCMTS core, all that is taking care of the DOCSIS MAC and upper layer protocols. So we already talked about the interface between the MCMTS core and the ECOM to handle the downstream phi to downstream MAC interconnection, and obviously when we move the upstream phi components, then we need to have an additional interface specification defined between the MCMTS core and the upstream phi, which is called upstream external phi interface. That has not been defined by KVLabs yet in terms of standardization. However, vendors like Cisco and other cable vendors are already working on coming out with the product which can have an external phi component for upstream as well. And in this case as well, as we know, DOCSIS timing server plays a key role. Otherwise we cannot acquire timing synchronization between the MCMTS core and the external phi components.
So just separating out both the upstream and downstream phi, and then you can move the work further out from the transmission system. Is that additional benefit of that?
So one of the benefits is today, if some of you are familiar with how the CMTS, integrated CMTS is, you would have the cable line cards, right, which comes with upstream ports as well as downstream ports. And a single system has got its own limitation in how many upstream and downstream cards you can keep adding. So by decoupling, you are getting into two advantages. You can have a large packet shelf where you can keep adding upstream and or downstream line cards depending upon your typical deployment requirements as it grows. And separating the downstream phi and upstream phi into separate line cards has got the advantage that depending upon your typical implementation, you might today have a need to increase the downstream capacity but not the upstream capacity. So you don't have to go for an integrated card which supports downstream as well as upstream. And again, this model supports vendor interoperability as well. So Cisco could be making the MCMTS core, and Motorola could be making the phi shelf, and then both are supposed to work together. So that is more advantage to the service providers, right? Does that answer your question?
Well, I was wondering about, is it not necessary to locate the elements of the CTS core on the device and separate out the work for each connection?
Probably not the timing server that can't be real long. That's got to be, I mean, when you talk about whether you've got UEI specifications that'll be in there.
Oh, is your concern about by separating them out, you could have some delay, latency, and timing issues?
I was envisioning moving the CMTS core physically further, not having to put it as close to the edge, close to the transmission system, if you separate out those elements of the phi. But as Paulie was pointing out, the timing server would be a problem in that service.
Yes, so the timing server has got some distance limitations, and because of that, typically you will have to have these gears in the same, pretty much the same location. But I think people are looking at the aspects of how we can achieve a scenario where core will be in one facility and the phi components would be another. So which probably would be something which should be taken care of in the future, because I keep hearing the customers asking about that option sometimes. And this is a DOCSIS 3.0 reference architecture for modular CMTS. I think some of the aspects we have already discussed. And what is shown here in addition is when you want to implement DOCSIS 3.0, you don't have to go with an MCMTS model. MCMTS model, we have seen that it lets you separate the MAC and PHY components. But you can even implement DOCSIS 3.0 by ICMTS, because say for example channel bonding, right, downstream channel bonding and upstream channel bonding to provide higher bandwidth capacity, which we'll talk about the details soon, can be implemented by an ICMTS too. So this just shows the reference architecture which coexists in MCMTS as well as ICMTS. And another thing which you might see here, new one, is something called an Edge Resource Manager, and we will talk about the Edge Resource Manager and its functionality in one of the upcoming slides. So what is listed here are the different MCMTS components. We have already talked about EdgeCom device and MCMTS core, and DTI or DOCSIS timing server is the timing server which provides DOCSIS standard timing information to the MCMTS components like MCMTS core and the downstream PHY shelf as well as upstream PHY shelf, etc. And DTI server typically provides a 10.24 MHz DOCSIS standard clock and 32-bit DOCSIS timestamp. So there is a protocol defined with DTI spec which is used to make sure that the synchronized timing information will be available to all the components. And the next one is the Edge Resource Manager, and the Edge Resource Manager provides some flexibility in terms of resource allocation. So when we talk about, as I mentioned earlier, an EdgeCom can support not only DOCSIS, right, because EdgeCom traditionally has been supporting the video streams. And now you are integrating the functionality for DOCSIS, HSD as well. And there could be a scenario where you might want to add and release channel resources on an as-needed basis. So today the way it is done with most of the implementations is by statically doing the configuration. So the static configuration on the MCMTS core as well as the static configuration on the ECOM. But it could be more efficient if there is a centralized manager which is available to keep track of the COM channel resources and all the characteristics of the COM channel resources, and there is a reservation and release mechanism available for the CMTS core to request for additional channel resources on an as-needed basis and release the resources, so that the same resource pool can be shared more efficiently as opposed to doing the static configuration. And that is taken care of by ERM or Edge Resource Manager, and it uses something called DOCSIS Resource Reservation Protocol to accomplish the same. Excuse me. So now here we are going to get into some additional details of DEPI. I think somebody asked about what is the physical interconnect. So this is how it looks like. So DEPI is implemented based upon L2TPv3. So the basic protocol used for DEPI is L2TPv3. And cable labs always prefer to make use of the existing protocols out there rather than reinventing the wheel. So they used L2TPv3 as the basic protocol, and all what it has is, we know that there should be a transport link from the MCMTS core to the EdgeCom to transport the DOCSIS MAC layer, the downstream MAC layer information into the EdgeCom, right? So the DEPI defines a pseudo wire between the MCMTS core and EdgeCom. And some of you who are familiar with L2TPv3 know that black is L2TPv3 access concentrator. So basically the pseudo wire gets created between the MCMTS core and the EdgeCom, and typically it's a GIGI link, and the converged interconnect network, which is shown in the middle, can be a layer 2 network or a layer 3 network, or it can even be a back-to-back connection. And it usually is a GIGI connection between the MCMTS core and the EEPROM. And the way the DOCSIS frames, layer 2 frames, are transported from MCMTS core to the EEPROM is, on the MCMTS core side, the frames will be encapsulated into L2TPV3 format, and then it is encapsulated over an Ethernet frame and sent across this link. And here let's take look at some more details about the DEPI. We have already seen that L2TPV3 is the base protocol used for DEPI, and DEPI uses two types of pseudo wires. One is called PSP or packet streaming protocol, and second is DMPT or DOCSIS MPEG transport. The difference being, we know that the DOCSIS layer 2 processing is done by the MCMTS core, and then it passes that information to the PHY shelf, right, EEPROM, so that it can do the PHY data functionality. But there are two ways it can be accomplished. If the DEPI is configured with packet streaming protocol mode, the DOCSIS frames are taken as it is and encapsulated into L2TPV3 and sent to the EEPROM, and the EEPROM will have to take care of splitting the frame into MPEG packets as well, because it has to be split into 188 byte MPEG frames, and before it does the CRC calculation for the MPEG, and finally it does the modulation and up conversion. And the DMPT or DOCSIS MPEG protocol transport, the CMTS code will take care of splitting the DOCSIS layer 2 frame into multiple MPEG packets, and the MPEG frames are encapsulated into L2TPV3 and sent via the pseudo wire. And from the signaling aspect, the DEPI supports, DEPI has got the control connection which needs to get established first, and the control connections may support one or more data sessions. So each session would be representing a connection going from the layer 2 to the corresponding QAM. And just to mention one more thing between PSP and DMPT, the advantage of going with PSP is PSP provides you the option with some additional QoS which can be implemented. Say for example, as we know, there are management messages, MAC management messages, as well as data frames which will be carried on a downstream channel, right? So the PSP, it can be implemented in such a way that for a particular pseudo wire which represents a QAM channel, when you say a QAM channel, it is a downstream PHY channel on the EEPROM, you can define different priorities for different types of packets. So DOCSIS MAC management messages may be provided higher priority and put in a higher queue, low latency queue compared to the rest of the data packets. But that is not available with DMPT mode of transport. Sure.
Sorry, a quick question. In one of your slides previously, when you talked about the Edge Resource Manager, you said it manages the QAM, yes?
Span tree?
Sorry, the Edge Resource Manager, you said there was an Edge Resource Manager
Right.
sometimes in the network, and you said it controls the channel usage, it controls the QAM, yes?
Edge Resource Manager is an optional piece, first of all.
If you use it, it doesn't use. Does it do it via the MCMTS, or does it have another connection directly to the EEPROM?
If Edge Resource Manager is in play, the Edge Resource Manager doesn't use the DEPI. The DEPI is the connection between the MCMTS core and the EEPROM device. So the Edge Resource Manager will be a server sitting somewhere which will have an out-of-band connection to the EEPROM as well as the MCMTS.
So is there an interface specification between the EEPROM and the Edge Resource Manager?
Interface specification between the EEPROM, yes. That is ERMI, Edge Resource Manager Management Interface. So if we quickly go back do you see that ERMI defined with the, let me move my cursor.
I see, yeah.
Does that answer your question?
Yes, thank you.
Now let us take a look at the DOCSIS timing interface. The concept is quite straightforward. There is a centralized DOCSIS timing server which provides timing information to all the individual components of the MCMPS architecture, and it provides 10.24 MHz DOCSIS standard frequency as well as the 32-bit DOCSIS timestamp. And it uses the physical connectivity between the server and the and modular CMTS components are UTP cables, which use RJ45 type connectors also, but a single cable pair is used. Single twisted pair is used for exchanging the timing information between the server and the client. It uses something called a ping-pong protocol and make sure that at a time only one person is sending the frame. So, some more information about Edge Resource Manager, so how it can be implemented. So with ERM, today even Cisco has started supporting the implementation of ERM Edge. The way it works is ERM keeps a database of the COM resources and also the channel properties of the COM channels. And then in order for a CMTS to request for resources, the CMTS should know what particular kind of resource I am requesting, right? Because it has to finally be available on a physical plant. So the plant topology information for the cable is available for the CMTS. And based upon the plant topology information, there is something called a service group which identifies all the channels available in a particular plant. And if the CMTS intend to add additional resources for a particular plant, it needs to it needs to know the service group, and then it provides the service group information and the characteristics of the COM channel it is looking for. So based upon that data, the ERM database should be able to pick up associated channels and try to reserve it for the CMTS. And DRRP or DOCSIS Resource Registration Protocol is used to accomplish the same. And it does two interactions happen, right? One is reservation and second is release. So that is why it's mentioned in this case, and also example is provided for the reservation case. Any more questions before we move forward into DOCSIS 3.0 details? I think we already talked about some of the motivating factors behind DOCSIS 3.0, and one is to provide increased channel capacity to account for the ever-increasing bandwidth requirements in the access network. Second is enhancing the security, and then the next one is expanding the addressability of the network elements by adding the support for IPv6 cable, and then eventually the need to deploy new service offerings with high data rates and things. DOCSIS 3.0 has got an extensive list of specifications which is defined for implementation, and it has got a set of core specifications and another set of related specifications. So for a full-fledged DOCSIS 3.0 implementation, so it has to comply with all these specifications which are listed here. All these specifications are available in the Cable Labs website for people who are interested in knowing the details. So channel bonding we briefly mentioned. DOCSIS 3.0 supports upstream channel bonding as well as downstream channel bonding. So it is nothing but combining multiple physical channel resources to form a single logical bandwidth pipe, so that your available capacity will be n times the number of physical channels available out there. Then with IP multicast, DOCSIS 3.0 introduces source-specific multicast, and it has introduced QoS for multicast, which was not available in the standards before, and payload header suppression. It's nothing but the repeating parts of the payload header can be suppressed to improve the efficiency in the transmission media. PHS was out there available for unicast transmissions with DOCSIS, but DOCSIS 3.0 has started supporting it for multicast as well. And QoS and authorization are another two aspects which are added with IP multicast support. And for IPv6, it supports provisioning for IPv6 addresses for CM management as well as for IPv6 support for CPEs as well. Any questions? We will look at some of the details of security in subsequent slides. And fiber also has a few enhancements. The major thing is upstream frequency range available for US DOCSIS was 5 to 42 megahertz, but today it can be extended up to 85 megahertz, providing more upstream channels in the plant. And there are certain DOCSIS 3.0 aspects like topology and ambiguity resolution which had to be introduced because of the fact that when you keep adding more and more downstream channel and upstream channel resources into the plant, when a cable modem is trying to initialize for the first time, the CMTS has no clue which fiber node a modem belongs to. And this has to be done through something called an ambiguity resolution. And DOCSIS path verify is some kind of health monitoring mechanism used to check the latency and packet loss. And from the management perspective, there are a lot of enhancements made with OSSI. The main thing is, in previous versions, IPDR was available only for reporting the usage, channel usage for the flows, but today IPDR schema has been defined for DOCSIS 3.0 for managing most of the aspects like proactive managing as well as reactive management. What is listed here are some of the important MAC management messages which are introduced in DOCSIS 3.0. This is not a complete list, but a few key ones are listed here. MBD or MAC domain descriptor message is one of the most important messages which plays a key role with DOCSIS 3.0 implementation. We will look at the details of the MBD in later on. And bonded initial ranging request, when the modem initializes for the first time when it is coming up. With DOCSIS 2 and prior versions it was ranging request or initial ranging request, but bonded initial ranging request is based upon whether it is part of a fiber node which supports channel bonding. And then there is the concept of dynamic bonding change. It's when a cable modem has been assigned with a particular bonding group. It represents multiple physical channels, right? And if there are reasons to switch the modem from one bonding group to another, say for example a 4-channel bonding group to a 2-channel bonding group, then the dynamic bonding change mechanism can be used to accomplish it. And it has got some additional functionalities which plays a key role in enhanced multicast support as well, which we will see when we go over the multicast section. So these are some of the different frames and headers introduced with DOCSIS. Because of the upstream channel bonding, so there are new headers introduced to support upstream channel bonding, something called a Q depth based request frame. We will see the details of it when we talk about upstream channel bonding. And another important extended header is downstream service extended header, which plays a key role in downstream channel bonding as well as multicast enhancements with DOCSIS 3.0. So continuing with the MAC layer new features, MBD or MAC domain descriptor message is a message periodically sent by the CMTS in the downstream direction, which DOCSIS 3.0 modems can understand and decode. So MDD provides a lot of information related to the initialization. MDD can be used used for ambiguity resolution, which we were talking about earlier, because when a CM is trying to initialize and come up for the first time in a complex cable plan which consists of multiple upstream channels and downstream channels, some of the channels from a mic domain would be available to one fiber node and some would be available to another fiber node, right? But CMTS or CM has no idea about which fiber node it is trying to initialize on. But this MDD message plays a key role in helping them do the ambiguity resolution and finally find out the right fiber node and set up downstream and upstream channels which is available for them. Again, the plant topology plays a key aspect, and resolving the plant topology and ambiguity resolution is done through the MAC domain descriptor message. Upstream and downstream bonding we already mentioned, but we will go through the details in subsequent slides. And downstream service extended header. So when we say extended header for the DOCSIS layer 2 messages on the DOCSIS frame header, the extended header is something which gets added on the standard header to provide additional information. So the downstream service extended header defines something called the downstream service ID or DSID and sequence number. And DSID typically represents a stream of packets, not necessarily a single service flow, not necessarily associated to a single modem, but typically a single modem would have one or more DSID corresponding to different streams of traffic. And the sequence number and DSID are used to resequence the packets when in the downstream direction packets are sent across multiple channels. And again, these are some of the new MAC management messages defined to centralize the control, provide additional control on the CMTS side to, say for example, remotely reboot the CM or disable the upstream temporarily as part of troubleshooting and things like that. And the attributes what you see here associated with bonding group, as I mentioned, a bonding group is a set of upstream or downstream channels, and they can be defined with attribute. And when service flows are defined for the cable modem during the initialization via the configuration file, they also will be defined with the attribute mask. So the attribute mask will be compared against the attribute to make sure that the appropriate bonding group will get assigned to a particular service flow for a modem. And multi-part registration request is because of the fact that there are so many enhancements in DOCSIS 3.0. A single registration request packet cannot encode all the TLVs during the registration, and it has to send it in multiple frames, and that is what is taken care of by the multi-part registration request. Receive channel profile finally is a way for cable modems to inform the CMTS about its receive channel capabilities. So we know that with downstream channel bonding, there could be a bonding group consisting of 4 physical channels or 5 physical channels or 6 physical channels. But some CMTS can only tune into 4 downstream channel frequencies, and there could be a capture bandwidth as well. These 4 frequencies need to be within certain capture bandwidth. And also whether it gets about 256 QAM or 64 QAM on a per QAM channel basis, and all those aspects will be provided by the receive channel profile information during the CM initialization. Any questions so far, or can we move forward? So, downstream channel bonding, the concept is very straightforward. It is something like an MLPPP like technology. So, all what you are doing is, instead of the cable modem using a single downstream channel or set of modems which are registered to single downstream channels, you are combining multiple downstream channel resources and that is formed into a single logical pipe. So for a particular service flow, a stream which goes from the CMTS side to the cable modem, the individual packets of the stream can be spread across these physical channels, and the DOCSIS, which represents the stream, and the sequence number will help the cable modem to resequence the packets before it sends to the customer premises network. And this is a schematic representation of how the channel bonding happens. Here, packets P1, P2 and P3 enters the CMTS in sequence, and using the downstream extender header, the DOCSIS and the sequence numbers are assigned, and we do have a bonding group consisting of channels D1, D2 and D3. 3 physical channels, and the packets are spread across these 3, right, because it's trying to make use of all the available physical resources, and the CM will do the resequencing based upon the DOCSIS value, downstream seek, as well as the resequencing index. I mean the packet sequence number. So the concept of MAC domain was out there with DOCSIS 2.0 and prior versions of DOCSIS as well. It is nothing but a CMTS sub-component which handles the MAC layer management of multiple downstreams and multiple upstream channels. Another key feature in DOCSIS 3.0 is MAC domain service groups, and all that does is it represents a MAC domain downstream service group represents the set of all the downstream channels from a MAC domain which are available physically to a modem. So typically for a physical fiber node in the plant, the MAC domain downstream service group for all the modems connected to the same fiber node would be the same. And likewise, we have the concept of MAC domain upstream service group as well. So MAC domain upstream service group means all the upstream channels which are available for a single modem to transmit into the CMTS, and it corresponds to a single MAC domain. And MAC domain CM service group or MDCMSG combines the upstream and downstream. It's the superset of upstream and downstream channels which are available in a single fiber node corresponding to a single MAC domain. So we talked about MDD earlier, that MAC domain descriptor message is a periodic MAC management message sent out in the downstream direction, and it is very helpful in topology resolution as well. And one of the things based upon the CMTS configuration which would be included in MAC domain descriptor message would be something called the MDDSSG, MAC domain downstream service group, and MDUSSG, MAC domain upstream service group. Along with that, individual frequencies which are part of the MAC domain also will be defined, and it helps the CMTS to, it helps the cable modem to identify which MAC domain downstream service group is available for it. And the important thing to keep in mind that first step would be to resolve the MDDSSG, MAC domain downstream service group, so that once it is resolved, the CMTS and the CM knows the set of channels which are physically available to the modem. And afterwards, during the registration, if the modem is going to be provided with a bonding group consisting of multiple channels, those channels would be a subset of that MAC domain downstream service group. That is what is shown in the schematic diagram here. And there is also this concept of primary capable downstream channels, we know that CMTS is the centralized controller, and CMTS sends lot of MAC management messages, and in response CM also sends MAC management messages to the CMTS. But a channel out of bonding group, one or more channels would be designated as primary capable channels. The responsibility for the primary capable channel is to send key messages such as DOCSIS sync message. Say for example, in order to establish the timing relationship between the cable modem and the CMTS, the sync messages needs to be periodically transmitted. The sync messages, then the upstream channel descriptor message which describe the characteristics of the upstream channel so that the cable modem knows when it tries to transmit what are the characteristics for the upstream channel, like the channel width and the modulation order it needs to use, and also the bandwidth map messages also would be sent on the primary capable downstream channels. So for a modem group, for a modem to get connected and established and come online, there should be at least one primary capable channel to which the modem is logged on to, which is typically the first primary capable channel. We already talked about the downstream service IDs. Downstream service IDs plays a key role in packet desequencing because it represents a particular stream, and DSIP also represents multicast flows. In fact, the advantage of using DSIP with multicast flow is a cable modem can filter the relevant multicast flows, filter or forward based upon the DSIP, because the CMTS uses signaling mechanism via the dynamic bonding change to let the cable modem know which are the DSIPs corresponding to multicast flows it needs to forward or filter. And in the DOCSIS 3 implementation of multicast, the CM doesn't have to snoop the IGMP or anything of that sort because the implementation is completely done on the CMTS. CM just follow the instructions from the CMTS and decide what to forward to the customer premises equipment and what to filter from the customer premises equipment. And if you know what a service flow is, like service flow is a typical traffic flow which represents the flow of packets in the upstream or downstream direction, and the DSIP is not typically related to service flows. Say for example, one modem may have multiple service flows and all of them get assigned with a single DSIP. Any questions on downstream channel bonding? Moving on to upstream channel bonding, here it works in a slightly different manner because the way the cable modems get bandwidth granted in the upstream direction is it has to request the CMTS first. And what it does in the case of channel bonding scenario is cable modem will request for bandwidth by using one of the upstream channels, and depending upon if the cable modem is part of an upstream bonding group, depending upon the utilization of the individual physical channels in the upstream bonding group, the CMTS will provide bandwidth grants telling okay how much data at what point in time, because it is a TDMA network, right? It can transmit across one or more channels, and that's how it works in a nutshell. And this slide just talks about what I mentioned just now. And prior to DOCSIS 3, we had two concepts. One was concatenation and the second was fragmentation. So if you have small size packets like 64 bytes or 128 bytes, and to account for the request grant latency involved, there was something called the concatenation support, wherein you will combine multiple packets into a single burst, so that you can, in a single burst, you can transmit much larger amount of data, and the CMTS will have to separate those packets. And the fragmentation was out there to take care of two things. One is to make sure that the large burst will not cause the voice, the time-sensitive packets such as void to be blocked. And the second one was to make sure that the upstream burst size itself has got its own limitations. So what would typically happen is if the cable modem concatenates multiple frames into a big burst, what the CMTs would do is, depending upon the burst size, it will provide band for the big burst consisting of multiple packets, but it would be in multiple fragments, so that this cable modem will end up fragmenting the packets as well in the upstream direction. Now, with the DOCSIS 3 or continuous concatenation and fragmentation, what happens is, as packets keep coming in from the CPE side, customer premises side, depending upon the depth of the queue. Say for example here, 1000 bytes represent, in this example, 4 packets. When there are 1000 bytes worth of traffic to be sent in the upstream direction, the CM will request, cable modem will request for 1000 bytes worth of bandwidth grant using one of the upstream channels. And the CMTS, depending upon the individual channel utilization, will provide bandwidth grants in segments, as you can see. So for example, the request was for 1000 bytes, but the grant was sent in 200, 300 and 500 across 3 channels. So the cable modem is not only concatenating the packets here, P1 through P4, and it ends up segmenting them and sending across the upstream channels. Any questions on upstream channel bonding? So some of the 5 enhancements here, as far as the bonding capability is concerned, a DOCSIS 3.0 compatible cable modem should at least support channel bonding in the downstream direction for 4 channels. That is the minimum requirement. And in the downstream direction. And in the upstream direction, again, it has to support 4 carriers. As far as the upstream frequency range is concerned, originally it was on DOCSIS 2.0 in prior versions, it was 5 to 42 megahertz, but it provides an extended frequency range to 85 megahertz, so that you have more upstream channels available in the DOCSIS 3.0 world. And they got rid of some of these smaller simple rates because the plan is today good enough to handle at least 1.6 megahertz of channel width for upstream. So DOCSIS 3.0 has eliminated anything under 1.6 megahertz. These supported ones are 1.6 megahertz, 3.2 megahertz, and 6.4 megahertz. And also in the downstream direction, from 85 to 860 megahertz range, it has extended the downstream spectrum range to 1 gigahertz. Any questions? Let's take a look at some of the enhancements done in DOCSIS multicast. So these were some of the works behind enhancing the DOCSIS 3.0 multicast. DOCSIS 3.0 has introduced the support of source-specific multicast or SSM and IGMP-v3, which were not available with DOCSIS 2.0, and IPv6 multicast support has also been introduced in DOCSIS 3.0, because in fact IPv6 unicast also was available prior to DOCSIS 3.0, so MLD, multicast listener discovery, is available with DOCSIS 3.0 support. And QoS for multicast was not standardized prior to DOCSIS 3.0, which is another one which has been introduced. And support for bonded multicast. We have been talking about bonding multiple physical channels, right? Even the multicast packets can be sent via a bonding group. And obviously the DOCSIS 3.0 maintains backward compatibility with DOCSIS 2.0 and earlier versions of DOCSIS for multicast. And another aspect is the DOCSIS 3.0 implementation of multicast can explicitly track the listeners, the way it is implemented. So prior to DOCSIS 3.0, the way the multicast was implemented was the CM would do something like an IGMP snooping, so that the CM knows which are the multicast groups, packets corresponding to which are the multicast groups, which it needs to forward from the RF side to the customer premise side. With DOCSIS 3.0, that requirement is taken out because CMTS centralized controls everything from the CMTS side. And the way the CM will come to know whether a multicast stream needs to be filtered or forwarded is based upon the information provided by CMTS via a dynamic bonding change messaging. So what happens is, if there is a multicast receiver at one of the customer premises, so if it sends a multicast report message, or once that multicast report message is seen by the CMTS, it knows that it has to join a specific group, or it could be a group specific source SSM IGMP v3 report saying providing the source address as well as the group. So based upon that, what the CMTS would do is CMTS would send a dynamic bonding change message with a DCIP corresponding to that multicast group packets, and also it will inform this cable modem about the MAC address of the listener or the receiver. So the cable modem knows that once it receives those packets with the DCIP defined for the multicast, it will forward it into the appropriate interfaces so that the multicast receiver will receive the packets. And this just shows the architecture schematically. So as you can see, the CMTS has IGMP, MLD, as well as CLI webconfig, and here what is happening is in the data path, the DCIP ladder packets are sent down. So the DCIP filter has already been established based upon the control path DCIP communication. That was the dynamic bonding change which informed the CMTS cable modem about which are the DCIPs corresponding to multicast it needs to receive and process. So accordingly, in the data path, when the DCIP ladder packets are sent down, cable modem DCIP filter will take care of filtering or forwarding the multicast streams correspond to the DCIPs, and then again some additional control data is provided by the CMTS. One way is to provide the explicit MAC address of the CPE is participating in it, and accordingly it will forward to the corresponding outgoing interfaces on the CPE side. Any questions so far on multicast? So what is listed here is whatever I explained in the previous diagram, how it does the filtering and forwarding. And CM modem is something called cable modem management interface, cable modem interface mask, which is another way for the CMTS to let the cable modem know that when there is a stream with particular DCIP comes, to which interfaces it has to forward and which interfaces it has to block the multicast when it does the replication at the CM level. And as you can see here, this is a bonding group consisting of two channels, downstream channel 1 and channel 2, and streams corresponding to two multicast groups represented by DCIP 1 and DCIP 2 are sent across both. And the first CPE here corresponding to CM1 joins only S1, G1, so the CM1 will only accept DCIP 1, packets corresponding to DCIP 1. And in the case of CM2, since CPE joins S2, G1, the CM2 would accept packets only corresponding to the DCIP 2.
And again, you said that the source to DCIP mapping is being done by the CMTS and then somehow communicated to the cable modem.
Right, so in the case of dynamic multicast scenario, because there's a static multicast also we look at it. So what happens is, if first of all the source, say for example, if CP wants to join S1, G1, what it will do is it will send a report, right? Report is going to reach by the CMTS. So the CMTS knows which stream it has to be sent to the CM1, right? And DCIP 1 is the DCIP representing that stream. Every packet will have that header information. In addition to that, the CMTS has two options. One, it can give the MAC address of the CPE which wanted to join. So since CM is like a bridge, it knows which is the outgoing interface for that MAC. So based upon the DC, it will accept the stream, and based upon the MAC address, it will know where to replicate it if there are multiple interfaces. And it supports IGMP v2, IGMP v3, MLD v1 and MLD v2. Everything is supported as far as multicast is concerned in DOCSIS 3.0. And as I mentioned, CMTS can track membership explicitly. So if it is IGMP v3, it can do it on a per CPU basis, but per CM basis for IGMP v2. The reason being, with IGMP v2, the host will participate in something called the report suppression. So when the host does this report suppression, the CMTS is going to get the report from not all the hosts, right? Only one of them. So that is why it can only track on a per CM basis. But in the case of IGMP v3, basically the host will not do the report suppression. In the SSM scenario, it is going to provide the report corresponding to a query every single source, so that it can track it on a per CPE basis. And this section just talks about how joins and leaves. In the case of, we have seen that how joins, right, and how it's going to leave is, if one of the hosts explicitly sends a leave message, then it will do a group specific query back to the in the downstream direction. And if there is no response for the group specific query, what will happen is it will have to delete the DC from that particular CM, right? So it will send a dynamic bonding change asking the cable modem to delete the DC so that it doesn't have to receive and transmit that multicast stream into the customer premises side. Static multicast, let's quickly touch upon that. It is something called an always on service. During the cable modem registration, you can use certain TLBs which are defined in DOCSIS to define the group, and in the case of source specific multicast, source as well as group for defining the static multicast. So you can have one or more groups like that. And during the registration itself, these groups are assigned to the cable modem, and corresponding DC values are assigned to the cable modem, and the cable modem and the CMTS would start transmitting the multicast streams corresponding to the source group there. And even if it doesn't affect any IGMP join or leave, anything happens because it's a static multicast. Any questions on multicast before getting into security? So the major aspects of security enhancements here are, in the case of DOCSIS 2.0 or prior versions of DOCSIS, the security configuration, the authentication and authorization and encryption to encrypt the data packets were done after the entire registration phase is complete. Cable modem initialization and the registration request response and the registration is complete. However, security enhancement here, you have the option to do something called an early authentication and encryption. That is, if you know the initialization process, right after the ranging is complete and before the IP connectivity establishment itself happens, the authentication authorization stage kicks in, and more often that point onwards, all the packets will be encrypted. So it doesn't have to wait till the registration time. And early authentication and encryption can be enabled or disabled on a per MAC domain basis, and some CMs may support or may not support this as well. And the MDD message, the periodic MAC management message sent out, has got a DLV encoding which informs the cable modems in that network whether it has to participate early authentication and encryption or not. And the other additional enhancements as far as security is concerned, the CMTS acts as a proxy for TFTP. for the DOCSIS file download phase during the initialization. DOCSIS file download is the phase during which it receives the configuration parameters which are defined in the backend provisioning server. During the DOCSIS file download phase, you have the option to define CMTS as a TFTP proxy, so that instead of cable modem being able to directly download the CM file from the server, the CMTS will intercept that. First, CMTS will download from the server, and the cable modem will have to download it from the CMTS, which acts as a TFTP proxy. So that way, the one advantage is CMTS can make sure that there is no tampering of file being done in the download process for theft of service. And there is something called as cable modem MIC and the CMTS MIC validation used for integrity check for the DOCSIS file, and then MD5 hash was used in prior versions, and multilinear modular hash or MMH is used with DOCSIS 3.0. And instead of triple DES, for encryption of data, advanced encryption standard or AES is a requirement. But triple DES needs to be supported for backward compatibility. And ARP-based limiting is a feature to prevent DOS attack, ARP-based DOS attack, which was already implemented by most of the vendors, including Cisco, but DOCSIS 3.0 has standardized it. And source verify to verify that when from the cable network, one CPE is transmitting some information, the IP address used by the CPE is a valid IP address. That is verified using the cable source verify feature. And if you are familiar with the X.509 certificates, which is used with DOCSIS 1.1 and later modems, with DOCSIS 3.0, it has introduced the certificate revocation option also. Just in case the keys are compromised or the certificate is compromised, so temporarily or permanently the certificate revocation can be done for those compromised keys and the associated certificates. So that is the certificate revocation, which is also introduced in DOCSIS 3.0 security. Any questions around security? I have a single slide on OSSI. So the major difference between DOCSIS 2.0 and DOCSIS 3.0 as far as OSSI is concerned, because of the overheads involved in SNMP management and the inefficiency, the DOCSIS 3.0 OSSI introduces IPDR. So IPDR was previously used with DOCSIS 4, providing the stream the statistics information for accounting purposes. But with DOCSIS 3.0, the IPDR schemas are defined for CM management, CMTS management, and all those aspects. So that is one major advantage, and it is expected to be much more efficient to transport or stream the management information for monitoring, health monitoring, and reactive management purposes using IPDR as opposed to SNMP. And CM diagnostic log is something which is introduced for flapping model, for example, keep track of the information and also provide that to IPDR. And enhanced signal quality monitoring is nothing but measuring periodically the RF level, signal to noise ratio, for example, and other aspects such as the FEC errors, uncorrectable FEC errors and things at the file layer, and then again provide via IPDR that information for management and monitoring purposes. So I think it will take another 10-15 minutes to just go through the IP V6 in cable section. So this is the last section which we are going to cover. So I know that it's going to be a little 10 minutes more time we are going to take. So here we will just give a brief overview of IPv6. I know that most of you are already familiar with it. I don't think we need to spend a lot of time on that. And we'll see what is the motivation behind cable operators in going for IPv6. And we'll take a look at the IPv6 in DOCSIS 3.0 environment, and also as theory of operations in DOCSIS 3.0 for IPv6. So as most of you know, the major difference is the size of the address space. It's 128-bit instead of 32-bit addressing. And it allows global assignment. You don't have to go with private addresses which are overlapping and then go with NAT and all that complicated aspects. And it is called smarter packet because the header format itself is simplified, as you know. Built-in security because IPsec has been mandated with IPv6 as opposed to IPv4, which was not mandatory. And the mobile IPv6 has got some enhancements in the definition. And I know that this flow label has not been completely defined on how to use it, but the expectation is the flow labels will play a key role in providing per flow basis QoS even when the entire packet layer payload is encrypted. So just a one-on-one comparison between v4 solution and v6. Addressing range we have already seen. As far as auto configuration is concerned, v4 solution is DHCP and v6 uses something called DHCP v6 version. However, with v6 we have a serverless auto configuration also available. And the security, it was optional with IPv4, then IPv6 it was mandated, and mobile IP is available in both the cases, but it is much more enhanced with v6. And quality of service, you can see that DiffServ and integrated serve services, it is similar to IPv4, but flow labels are introduced with IPv6. And IP multicast somewhat similar, but instead of IGMP, we have MLT or multicast listener discovery protocol, which is handling it. And IP anycast, there was no concept of anycast with IPv4, but we do have with IPv6. Anycast, if you don't know, is nothing but multiple destination devices will be assigned with the same IP address. And if someone has to send an information, one of the destination devices will receive the data. As opposed to multicast, where the group of devices, everybody will be receiving the information sent to that particular address. Just a quick look at the difference between the v4 header and v6 header. As you can see, the IPv6 header is much more simplified. Even though the header has a standard size of 40 bytes, the source address and destination address are taking up a total of 32 bytes because they are 128 bits address spaces, right? Then only 8 bytes is available for the rest of the header options. And traffic class is similar to the type of service. And then you have the flow label, which is introduced, 20 bits flow label, which we were talking about before, to provide additional QoS support. And there is no header length, but payload length is another aspect which is introduced with IPv6. And next header is something similar to the protocol field, but here the difference is IPv6, even though the first packet header is 40 bytes size, it can have n number of optional headers before having the higher layer protocol header. So the next header field will define what is the next header. It can be an options field or it could be a next layer protocol header. Hop limit is similar to the time delivery, but a different name has been given. So the motivation for cable MSOs, mainly it was the address depletion, and especially when they started using digital set of boxes which were assigned with IP addresses and introduced the voice over cable support, which again requires additional IP address space. So they started running out of IP address space. So obviously they had to look at going with the option for implementing IPv6. And managing through the industry consolidations when larger MSOs were acquiring the smaller tier 2 MSOs, obviously there was some address overlapping which was causing additional management complexities. And increased the demand from the consumer side for IP address as well to support the plug-and-play operation for a home network. And the need to get rid of the NAT as much as possible, right? So if you are using IPv6, you don't have to go with NAT. So here, the convergence of data, voice, video and mobility, everything is obviously going to increase the requirement of additional address space. And with industry consolidation, so there's going to be address conflict, right? Then the way to go would be to go with IPv6 addressing. And in home networking, so if you have a home router which supports address delegation and DHCP, you can have the home router delegating the address space /48 from the CMTS side, and it automatically assigns the addresses to the individual devices in a home network. So getting rid of NAT for global transparency, and access transparency through mobile IPv6 support. So we already discussed the rationale behind going for IPv6 support for DOCSIS 3.0, and there were two phases proposed, phase 1 and phase 2. And with phase 1, the support requirement was to provide CM provisioning and management over IPv6. And phase 2 addresses IPv6 support for CPEs as well. And another thing to keep in mind is you can have a cable modem with a built-in lightweight router functionality, and in that case, a /48 prefix can be delegated to the lightweight router built in the CM, and the CM can take care of address assignment to the individual devices in the customer network, either through serverless auto configuration or through DHCP.
There was debate about the /48 mandate and integration. It's almost like one concept and saying about this three. There's a specific prefix line. You're saying that this three imposes a specific prefix line? Like /48 on the customer side.
I can't hear you well.
He's asking if the /48 is an example or whether that's actually in a specification that's in DOCSIS 3.0.
Oh, okay, so /48.
There was debate about small site concept to move from 48 to say 56.
Right, /48 is just an example like that.
So that's not the specification, correct?
Yeah, it's not the specification, it's more of an example. Now let us take a look at the theory of operations. Mainly it's on the provisioning side. So as far as the IPv6 support is concerned for the cable modems, so you can have three different modes of operation. So in a DOCSIS 3.0 environment, whether the IPv4 is supported or whether a cable modem needs to support IPv6 or no is communicated by the CMTS through the MDD message again, the MAC domain descriptor message. So with the MDD message, there are settings in the MDD message which will tell the cable modem to go with IPv4 only mode or IPv6 only mode or dual mode. Dual mode is where it can have a dual stack supporting IPv6 as well as IPv4. So this is the flow. Layer 2 provisioning is where the MDD message will inform the CM about whether it has to use IPv4 or IPv6 or dual mode. Then the next step would be acquiring the IPv6 connectivity. And the rest of the provisioning is similar to the DOCSIS 2.0 style, where you obtain the time of day and obtain the configuration file and eventually complete the registration. So let's take a quick look at the flow here. So first of all, an MDD message, which is nothing but the periodic message in the wire, right in the downstream direction, tells what kind of V6 or V4 provisioning mode it has to use. Okay, here it. So the very step, first step, because it's going to be an IPv6 node, would be the link layer address assignment, because it has to be assigned itself with a link layer address, right? Which has got the link local scope before it can proceed further with even the DHCP v6 phase. So this is based upon the RC. It uses the well-known link layer prefix FE80:0 plus the EUI which it makes by taking the MAC address and sticking in that FFFE or whatever in the middle, and comes up with the link layer local address. And the next step, after the link local address has been created by modem, then it has to go through a duplicate address detection through neighbor solicitation and neighbor advertisement. And typically it is not expected to get a response for the duplicate address detection, but it may however happen if there is a duplication of MAC address by due to a theft of service of some other cable modem having that. So typically no responses will be expected for the first DAD. Then the next step is router discovery, right? So in the router discovery phase, it sends a router solicitation message which will be received by the CMTS. And CMTS will respond back with a router advertisement. The key is in the router advertisement, the CMTS will have the M and O bits set indicating that it has to go with the stateful auto configuration, which is DHCP-v6. And then the DHCP process kicks in. So first is the solicit message looking for the available DHCP servers, which obviously the CMTS is acting as a DHCP relay agent, which will forward to the DHCP, one or more of the DHCP servers. DHCP reply received back the advertised message from the DHCP server will be forwarded back to the cable modem, and the cable modem will send a request message, and eventually it has to get a DHCP reply. And finally, there should be a confirm which is going back to which we missed adding that over here. However, after the address has been assigned, the global address has been assigned, it has to go through another step of duplicate address detection. But if the DAD did not happen in the first case, it's not going to happen in the second case either. And what is shown here on the right is the advertise and request can be optional, because if the modem is willing to do the rapid commit, when it sends the solicit, it uses the appropriate settings in the solicit message to say that it is willing to do the rapid commit. In that case, the advertise and request stage will be skipped, and it will go to the reply immediately for the solicit message, and it will be assigned with the address. The TOD phase is part of the regular DOCSIS registration, occurring for time of day, and TFTP is the file download phase for the DOCSIS file, and eventually it sends the registration request and get registered. So the dual stack management, we talked about the option for a cable modem to have an IPv6 address as well as IPv4 address. So in that case, after the modem has acquired IPv6 and IPv4 addresses, then it would be able to be managed by using an IPv4 or an IPv6 address from the MSO's management network. Another mode is alternate provisioning mode. This is more for improved reliability. So in this case, the MDD message will say that ask the modem to go with alternate provisioning mode. It will try to do IPv6 based upon whether the setting is for IPv6 to be tried first. And if that fails, then it will fall back to IPv4. So these are the requirements for the CMTS when it comes to support for IPv6. CMTS can be a bridge or router, and it has to act as a relay agent for DHCP-v6 messages, the same like the IPv4 implementation, and it participates in network discovery. So the neighbor solicitation messages, it will send back in the downstream direction to facilitate the neighbor solicitation and neighbor advertisement as part of DAD and the address resolution. and it generates counter advertisement messages to vast cable network. And for multicast, any source multicast, source specific multicast, both are supported in the IPv6 implementation. As far as requirements for this cable modem is concerned, as we know, DHCP-v6 address allocation mechanism must be supported. APM and dual stack mode, alternate provisioning mode and dual stack mode, which we discussed, is to be supported. And if dual stack mode is supported, the management has to happen either via or SNMP for IPv4 or IPv6. And regardless of the provisioning of the cable modem is V4 or V6, it is supposed to transparently transmit IPv6 data from the CPEs. And if the cable modem has got a built-in router functionality, then it has to support serverless auto configuration. This is where we will do the prefix delegation, get the prefix, and then we will go with the either DHCP based or serverless auto configuration option. That is very much it on the IPv6, and it covers the entire session too. Sorry it took a little extra time. Any questions on any of the topics we discussed here?
I have a question about, something wasn't brought up, but is there a specification in DOCSIS 3.0 for MCU, for IP MCU for the CN of the cable of the DOCSIS channel?
I don't think it explicitly specified about the MTU, but as you know, the minimum MTU for IPv6 is 1280, right? So then if you want anything more than 1280, then you have to go with the path MTU discovery. Because typically DOCSIS 3.0 DOCSIS spec always, when they try to make use of RFCs and other things, they stick with what is already standardized there, until unless there is an explicit reason. So I don't think there is anything explicitly mentioned about MTU size, but I would think this is the case as part of standard IPv6 spec. Any other questions? How many of you are from cable background? Just okay. Thanks everyone.